Hello students, welcome to this lecture on adaptive filters. Recall that the LMS algorithm is based on minimizing the instantaneous square error square n with respect to the filter coefficient vector Hn. The filter weights are updated according to this equation. H of n plus 1 is equal to Hn plus mu times En into Yn. Yn is the data vector, mu is the step length parameter. The above is a stochastic difference equation. Therefore, convergence analysis is difficult. Our knowledge of deterministic convergence cannot be applied here. This lecture will concentrate on the convergence analysis of the LMS algorithm. Let us recall the SDA iteration. H of n plus 1 is equal to Hn plus mu times Rdy minus Ry into Hn vector, where Rdy is the cross correlation vector and Ry is the autocorrelation matrix. Under proper choice of step size mu, the filter coefficients converge to the winner solution, that is, as n tends to infinity, limit of Hn is equal to H optimum, and that is given by Ry inverse into cross correlation vector. And for convergence is given by mu lies between 0 and 2 by lambda max, and a simpler condition was mu lies between 0 and 2 by m into Ry 0, where m is the length of the filter. Can we extend these results to the LMS iteration? Let us try to answer this. Consider the LMS filter update equation H n plus 1 is equal to Hn plus mu times En into Yn. As it is a stochastic difference equation, the convergence analysis of SDA cannot be directly applied. So, the answer to this question is that the convergence analysis of SDA cannot be directly applied. The convergence problem has to be considered as the convergence of a sequence of random variables. This Hn sequence is a sequence of random variables. We consider such convergence while defining the consistent estimators. There are different modes of convergence for the sequence of random variables. So, particularly we considered convergence in probability and mean square convergence. Here also we will try to apply mean square convergence. As there is a unity feedback loop here, this coefficient here is 1, there is additional difficulty in the convergence analysis. We have to make one important assumption, that is independence assumption. Though the LMS algorithm is very simple, the convergence analysis is quite complex. To simplify the analysis, the independence assumption is made. The data vector Yn is statistically independent of past data vectors. This is the assumption. Such an assumption is not correct, because all data vectors will be dependent only. However, the theoretical results obtained using this assumption match reasonably well with the experimental results. Now, consider the filter update equation. Hn is equal to Hn minus 1 plus mu En minus 1 into Yn minus 1. Here Hn depends on Hn minus 1, which is function of past data, and it depends on E of n minus 1 and Yn minus 1. So, that way it is independent of yn, because yn is anyway independent of yn minus 1 according to independence assumption. Because of the above assumptions, we can separate out expectation. For example, we can write E of H transpose n into yn will be equal to E of H transpose n into E of yn. So, this type of separation will be needed in our analysis. First, let us see the convergence of the mean of the filter coefficients. When iterations proceed, whether the mean of the filter coefficients converge. Under the independence assumption, the LMS iteration is convergent in the mean if the step size parameter mu satisfy the condition, that is mu lies between 0 and 2 by lambda max. This is same as the SDA condition. We will prove this. H of n plus 1 is equal to Hn plus mu times En into Yn. Therefore, expected value of E of Hn plus 1 is equal to E of Hn plus mu times expected value of Yn into En. That is equal to E of Hn plus mu times E of Yn into error is Dn minus Y transpose n into Hn. Now, I can separately take the expectation here. So, therefore, the expression will be equal to E of Hn plus this quantity will be R dy, that is the cross correlation matrix, and this part will be mu times E of Yn into Yn transpose into Hn. Now, we will make the independence assumption. Assuming Hn to be independent of the data vector, we will get E of H of n plus 1 is equal to E of Hn plus mu into R dy. Now, here we will write this entire expectation is product of two expectations, that is mu times E of Yn transpose into E of Hn. And this quantity is now E of Yn transpose is the Ry matrix. Therefore, this will be E of Hn plus mu into R dy minus mu times Ry into E of Hn. Therefore, the average value of H of n plus 1 is equal to average value of Hn plus mu R dy minus mu times Ry into E of Hn, average value of Hn. So, this is same as the iteration for the SDA algorithm. Hence, the mean value of the filter coefficients satisfy the steepest descent iterative relation, so that convergence analysis of the SDA can be applied. Thus, the LMS iteration of the mean of the filter coefficients converge if mu lies between 0 and 2 by lambda max. So, if we consider in terms of the mean of the filter coefficient, then the iterations will converge as long as mu is between 0 and 2 by lambda max. In practical situation, knowledge of lambda max is not available or it is difficult to obtain. Therefore, we can consider trace of Ry instead of lambda max like in the SDA method. So, therefore, the conditions for convergence is mu should lie between 0 and 2 by trace of Ry, and trace of Ry is equal to m times Ry 0, that is the tap input power of the LMS filter. The LMS algorithm is convergent in the mean if the step size parameter mu satisfies the condition mu lies between 0 and 2 by m times Ry 0. So, that way we have to choose a value of mu which is less than this quantity. If we select a too small value of mu, then convergence will be slow, whereas a big value of mu will result in larger fluctuation from the mean. Choosing a proper value of mu is very important for the performance of the LMS algorithm. In addition to the above, the rate of convergence depends on the statistics of data and is related to the eigenvalue spread of the autocorrelation matrix that we have discussed earlier. This is defined by the condition number of Ry, which is lambda max by lambda mean. Therefore, rate of convergence will depend on k. K should be small. The fastest convergence of the system occurs when k is equal to 1, corresponding to the white noise. So, this condition also implies that the fastest way to train an LMS adaptive system is to use white noise as the training input, because in the case of white noise all eigenvalues are equal, therefore, lambda max by lambda mean will be equal to 1. As the noise becomes more and more colored, the speed of training will decrease. The average of each filter tap weight converges to the corresponding optimal filter tap weight, but this does not ensure that the coefficients converge to the optimal value, because only average part is converging. We have to consider the fluctuating part also. Let us consider the LMS difference equation. H of n plus 1 is equal to h n plus mu E n into y n. We have seen that the mean of LMS coefficient converges to the steepest descent solution. The mean will converge to the steepest descent solution. But this does not guarantee that the mean square error of the LMS estimator will converge to the mean square error corresponding to the winner solution. There is a fluctuation of the LMS coefficient from the winner filter coefficient. Because of random updating, Hn will be fluctuating from the winner solution H opt. Let Hn be equal to H opt plus delta Hn, where delta Hn is the fluctuation and H opt is the optimal winner filter impulse response. That is, H opt is the optimal winner filter vector. The instantaneous deviation of the LMS coefficient from H opt is given by delta Hn is equal to Hn minus H optimum. Therefore, mean square error, this is the mean square error MSE, is equal to E of square n is equal to E of dn minus H opt transpose into yn minus delta Hn transpose into yn whole square. This is the mean square error. Now, this part is the error due to optimum winner filter. We denote it by E opt n, therefore, mean square error will be E opt n minus delta H transpose n into yn whole square, and this we can write like E of square n, that is the winner mean square error epsilon mean, plus E of square of this quantity delta H n into yn transpose into delta H n, because these are matrix. So, this square term will come like this, minus the cross terms, that is twice E opt n into delta H transpose n into yn. So, that way we get it as, that is mean square error of winner filter plus E of delta H n into yn transpose into delta Hn minus 2 times E of n into delta H n transpose into yn. So, that way we can write that is MSE is equal to winner filter mean square error plus E of delta H n yn into yn transpose into delta Hn, because this term will become 0 because of the independence assumption. We can write that this deviation, first we can write this expression is equal to twice E of delta H n transpose into E of n into yn vector. We can write like this, because of the independence assumption we can say that this is the deviation and this deviation is independent of data. Therefore, we separate out the expectations. Now, this part error is orthogonal to data. Now, this expression will become 0. Now, mean square error will be simply epsilon mean, that is the mean square error corresponding to the winner filter plus this term. This is the excess mean square error. Therefore, there is an excess in the mean square error that is given by E of delta H n transpose into yn transpose into delta Hn. So, how to analyze this excess mean square error? The mean square error, that is epsilon infinity at convergence, is given by epsilon infinity, that is the mean square error as n tends to infinity, is equal to epsilon mean, that is the mean square error corresponding to the winner filter, plus epsilon excess infinity. This is the excess mean square error. An exact analysis of the excess mean square error is quite complicated. If excess mean square error converges as n tends to infinity, then En will also converge, because if this part converges, this part will be also converging. That excess mean square error can be determined using the independence assumption and other approximation, and the following results may be established. We will not establish it, but this is a very important result. Under the independence assumption, the MSE epsilon n converges if and only if mu lies between 0 and 2 by lambda max, and summation of, this is the additional condition, summation mu lambda I divided by 2 minus mu lambda I going from 1 to m is less than 1. Not only this condition is to be satisfied, this condition also is to be satisfied. And under that situation, the mean square error, that is equal to limit of epsilon n as n tends to infinity, is equal to epsilon mean, that is the mean square error corresponding to winner filter, divided by 1 minus summation mu lambda I minus 2 minus mu lambda I going from 1 to m. Therefore, this is the mean square error corresponding to the LMS winner filter. Now, we can find out the approximate value of excess mean square error, that is epsilon excess infinity, that is the excess mean square error at convergence, is equal to epsilon infinity, that is the mean square error, minus the winner mean square error, equal to epsilon mean, that is the winner filter mean square error, multiplied by summation mu lambda I by 2 minus mu lambda I going from 1 to m, divided by 1 minus summation mu lambda I divided by 2 minus mu lambda I going from 1 to m. We will make now some assumption, some simpler approximation. Suppose this quantity is much smaller than 1, then denominator will be simply 1, so that we can write epsilon excess, that is the excess mean square error, is equal to epsilon mean times summation mu lambda I divided by 2 minus mu lambda I going from 1 to m. This epsilon excess divided by epsilon mean, this factor which is equal to summation mu lambda I divided by 2 minus mu lambda I going from 1 to m is called the misadjustment factor MF for the LMS filter. So, there will be an excess amount in the mean square error by this factor. Further, if mu is much less than 2 by lambda max, then excess mean square error can be approximated by this relationship epsilon mean into mu by 2 into trace of Ry, because here this term becomes 1 and this becomes summation lambda I, and which is equal to trace of Ry matrix. So, that way misadjustment factor will be now mu by 2 into trace of Ry. This is the misadjustment factor for the LMS filter. Let us consider the example in the last lecture. The input to a communication channel is a test sequence given by xn is equal to 0.8 x n minus 1 plus wn, where wn is a zero mean unity variance white noise. This channel transfer function is given by hz is equal to z to the power minus 1 minus 0.5 into z to the power minus 2, and this channel is affected by white Gaussian noise of variance 1. Now, new questions are, in addition to last time questions, find the bounds of LMS step length parameter for the convergence of the mean square error. Find the excess mean square error and the approximate misadjustment factor. Here Ry we have already found out, that is equal to this matrix 2.255, here diagonal is 2.255 and off diagonal is 0.533, 0.533. Therefore, its eigenvalue we can find out, lambda 1 and lambda 2 are 2.79 and 1.72 respectively. This is the maximum eigenvalue. Mu should be less than 2 by lambda max, and that is less than 2 by 2.79. We choose mu should be small for excess mean square error. So, we take mu is equal to 0.01. This is less than this quantity. Then we see this factor, that is we want to determine the excess mean square error. Therefore, this factor we have to determine summation mu lambda I divided by 2 minus mu lambda I going from 1 to 2, here m is 2, and this we can find like this. Mu we know mu is 0.01, lambda 1 is 2.79 divided by 2 minus 0.1 into 2.79. Similarly, mu lambda 2 is 1.71, therefore 0.1 into 1.71 divided by 2 minus 0.1 into 1.71, and this factor is less than 1. Therefore, our choice of mu is right. And excess mean square error we can now determine. So, excess mean square error will be determined by this expression. So, epsilon mean Wiener filter mean square error, that we can determine from the Wiener filter solution, and this is given trace of Ry we can determine. So, we can determine the excess mean square error. Now, the misadjustment factor is given by excess mean square error divided by the optimal mean square error, and that is equal to mu by 2 into trace of Ry, and when we put mu is equal to 0.1 and trace of Ry is equal to sum of the diagonal elements, that is equal to 4.51 divided by 2, and that is equal to 0.225. That is, there is a misadjustment of 22.5% from the optimal mean square error. Let us discuss the drawback of the LMS algorithm. Here convergence is slow when the eigenvalue spread of the autocorrelation matrix is large. That is one important factor. A misadjustment factor is given by that is excess mean square error divided by the winner mean square error, that is approximately equal to half of mu times trace of Ry, and if mu is large, this quantity will be large. This error will be large unless mu is much smaller. Thus, the selection of step size parameter is crucial in the case of LMS algorithm. When the input signal is non-stationary, the eigenvalues also change with time and selection of mu becomes more difficult. We will see how these drawbacks are overcome in the next lecture. Let us summarize the lecture. Though the LMS algorithm is very simple, the convergence analysis is quite complex. To simplify the analysis, the independence assumption is made. That is, Yn is statistically independent of past data vectors. The theoretical results obtained using this assumption match reasonably well with the experimental results. Under this assumption, the LMS algorithm is convergent in the mean if the step size parameter mu satisfy this condition. 0 is less than mu is less than 2 by lambda max, or simply mu lies between 0 and 2 by m into r by 0. Under the independence assumption, the MSC epsilon n converges if and only if these two conditions are satisfied. Mu lies between 0 and 2 by lambda max, and this additional condition is summation mu lambda I divided by 2 minus mu lambda I going from 1 to m must be less than 1. And under this situation, the mean square error at infinity is given by epsilon mean divided by 1 minus summation mu lambda I divided by 2 minus mu lambda I going from 1 to m. This is the winner filter mean square error. Now, the excess mean square error is given by epsilon excess. This is the excess mean square error is equal to epsilon mean times summation mu lambda I divided by 2 minus mu lambda I going from 1 to m. And the misadjustment factor is given by, that is excess mean square error divided by epsilon mean, that is approximately equal to half of mu times trace of Ry. Thank you.